So 1111, the main things that we need to talk about from the 1111, we'll do a little bit with the binomial formulas and whatnot next time. And on Monday's class, we're really going to be talking about the Taylor inequality and error. So when you use a Taylor polynomial or a Maclaurin polynomial, instead of the full series, right? Of course, these things are not equal. And so the question has to be asked, well, how much are they off by? And that's the question that's answered by the Taylor inequality that talks about how much error, if you kind of stop instead of going all the way to infinity, after all, who would want to, right? If you just stop after 10 terms or so, how accurate is your result? The main things that we want to talk about in today's class are some of the applications that go along with the Maclaurin and the Taylor series. And so the main problems that we need from 1111 to kind of think about is this one here. We're going to do some evaluations with limits. So stuff like this. It turns out these are things that sometimes you can use L'Hopital's rule as well to solve these, but they may take many iterations of L'Hopital's rule. And so if you use kind of some of these Taylor-Maclaurin series, not only is this very clever, but it can also solve the problem faster sometimes. Another thing is that we saw in 11.2, right, the only time that we could really say what a series converges to, right? We did this a little bit in 11.2, and then we shifted our focus and we said, well, this is really hard to say what it converges to. So we're just going to say whether it converges or not, right? Does it go to some finite number or does it go to infinity or something like this? And so now with these Taylor and Maclaurin series, if we look at the series and actually relate it to a function that we know the Taylor or Maclaurin series expansion for, then we can actually evaluate out some of these series. So something like this. Right here, we can see that this is just actually a clever rewriting of e to the x, where you're plugging in 2 everywhere you see an x. So therefore, this is just going to correspond to e squared. So this actually converges, and better yet, we can say what it converges to. It converges to e squared. And now notice that this is not a geometric series. So this is a significant upgrade here. Likewise, stuff like this. Here's another one of these examples where we're going to be evaluating out, some infinite series. And now we can actually confidently say what it converges to. Okay, so those are the big problems that we need from the video, I believe. I don't think, yeah, so this gets into the Taylor inequality. So yeah, I'm not missing anything. So again, we're going to be talking about the Taylor inequality and stuff in Monday's class. So of course, consequently, right, the quiz coming up next Tuesday will not have the Taylor inequality stuff on it. Anything about the error and all that sort of stuff. But the quiz will cover, the 1110 and today's class as well. So, all right, let me switch over here. And it looks like there's at least one hand raised. Let's call on a few folks with questions, and then we'll get into the new problems for today. Michael, you got the floor.
Hey, how's it going, Professor McCombs?
Oh, excellent. How about yourself?
Good. So just for clarification, on Tuesday's quiz next week, it'll cover 11.9 and 11.10 and maybe bits and pieces of 11.11.
Yeah,
Am I right in saying that?
What we're doing today would be fair game. That's true.
Oh, okay. Thank you.
Yeah, definitely. Good. Any questions in the Q&A or the chat, Yuan?
Yeah, one is asking about the exam drop.
The exam drop?
Yeah. Do they have an exam drop?
Yes. So in the syllabus, the lowest midterm exam is replaced with the score from the final exam. So it's dropped and replaced with the score from the final exam if it helps your grade. So if it doesn't help your grade, then that doesn't happen, right? It's not going to lower your score. But if it helps your score, so if you do well on the final, right, or if you had to miss an exam for any reason, then that score gets dropped and replaced with your final exam score. Good. So today's goals, again, this kind of spans a little bit of 1110 and 1111, is we're going to continue to determine what some non-geometric series converge to. We're going to evaluate out some limits, faster than with the L'Hopital's rule. And we're going to be able to evaluate integrals of functions that do not have elementary antiderivatives. And so this last one right here is actually the one that I think is the most important. Because, you know, despite all of our chapter 7 knowledge, we can integrate quite a few things now, but there are some things that you just can't integrate. And in fact, there was a Piazza post earlier today about this, and, you know, one of the main uses for the Taylor and Maclaurin stuff. We talk a little bit about sine of x over x, and this doesn't have any elementary antiderivative. And so with the Taylor series, we can actually evaluate out some area under the curve. So let's get to it. Starting off here with the number e. This is Euler's constant. And so he calculates it out himself to quite a few digits, right? And he says, okay, and this is, you know, his actual text, what he wrote down when he was, you know, kind of publishing and all that. And then he goes on to say, if you want to calculate it out at home, and maybe you want more decimals, you want a better approximation or something like this, here's how you would actually go about this, right? And so I'd like to show that this is accurate. And so just as we did in the videos, we'll see that there are plenty of times where you want to align some of this information in the table, right, about the Maclaurin series with, you know, something that you have like this, and you can actually figure out what some series converge to. So in particular, I'm going to start with e to the x, and this is summing up from n equals 0 to infinity, x to the n divided by n factorial. Remember, the radius of convergence for this is infinity, right? It converges everywhere. And so if I was to go ahead and write out a first few terms of this or so, you know, when n equals 0, n equals 1, n equals 2, well, let's just do this. So I'm going to have x to the 0 divided by 0 factorial. Then I'm going to have x to the first power divided by 1 factorial. Then we're going to have x squared divided by 2 factorial. And then I'm going to have x cubed divided by 3 factorial. That's probably enough. Of course, it goes on forever. But again, this is what e to the x is equal to. And then if we go ahead and maybe we can simplify with one more line here, anything to the 0 power here is going to be 1. And if you divide that by 0 factorial, well, 0 factorial is also 1. Here you have x divided by 1 factorial, which is again 1. Here you have x squared divided by 2 factorial, which is 2 times 1. And here's x cubed divided by 3 factorial, 3 times 2 times 1. And so now notice, basically you can see Euler knew this here. And these are exactly lining up. For instance, you can see the one out in front here. I guess I need to use a different color than blue to highlight. One here, one here. These are looking pretty similar. These are looking pretty similar. The fourth term there is looking pretty similar to this one, right? We have a 1 times a 2 times a 3. Here we have a 3 times a 2 times a 1 in the denominator. All that's left is to just replace, instead of x, let's go ahead and plug in a specific value here. So instead of x, I'm going to go ahead and plug in the number 1. Of course, when you take 1 and you square it or cube it or anything like that, notice that this numerator stays as 1. And so there is you can verify that, yes, Euler knew what he was talking about there, that if you expand this out and keep on going, right, this does give you as good of an approximation as you could ever want for E. All right, let's see maybe one more of these. Here's an example of something that I've seen, you know, in previous like quizzes or exams or stuff like this. Find the sum of this series. So you can see already with the factorials below here that this is not going to be a geometric series. If this was a geometric series, right, we know how to figure out the sum of those. That's the whole a divided by 1 minus r sort of business, right? But here, sadly, this doesn't exactly line up. So we're going to try to figure out the pattern for this and put it in sigma notation, right? So for instance, I see in the numerator, it looks like we have more and more of these natural logs of 2, right? Here we don't have any. Here we have 1 natural log of 2. Here we have 2 natural logs of 2. Here we have 3 natural logs of 2. So it seems to me, if we're adding up, starting at 0 and going on, right, that we have so many of these natural logs of 2. First we have 0, then 1 of them, then 2 of them, then 3 of them, and it just keeps on going like this. So I'm going to do natural log of 2 raised to various powers, right? First to the 0th power, then to the 1st power, then squared, right? Because n ranges between 0 and it keeps on climbing, going off to infinity. In the denominator here, we can see that there are some factorials going on. Here, this one, you don't see it, but this would be the same thing as 1 factorial. And if you really wanted to fit the pattern and everything, this would be the same thing as 0 factorial, right? 0 factorial is also equal to 1. So it does seem like whatever the value of n is, we have that value factorial in the denominator. And then lastly, I'm missing one more thing. What am I missing? Yeah, the fact that it's alternating, right? Starting off with a positive, then a negative, then a positive, then a negative. And so I'm going to include this alternating piece and double check, right? If I plug in 0, it should start off being positive. Good. If I plug in 1, it goes to negative. Excellent. So on and so forth. And now this game pretty much always ends with going and looking at that table, right, that we had in our video notes. So I might as well have this pulled up here just so we can look at this. Or if this was on an exam or whatnot, right, you would pull this up on the formula sheet for the exam. And you would take a look at this and you would say, okay, well, which one of these here does what I have most closely align with, right? And so I'm just kind of looking at all these sums and comparing. Now notice these all have x's in them, so I'm going to have to substitute in something for x, but I'm just trying to figure out which one of these most resembles what I have. So in particular, right, we can go down the list and kind of start excluding some stuff. So this one right here, this has just x raised to various n's, but it doesn't take into account this factorial business, right? There's supposed to be a factorial in the denominator. So that one's out. What about e to the x? E to the x is looking pretty good. It doesn't exactly line up with what I have necessarily, but I like the fact that we have something raised to various powers of n, and we have division by n factorial. So I like that one the best, but let's just maybe keep on going on this one time and kind of look at all the others. I would say sine of x is out because it only has odd powers, right? So this is the x to the 2n plus 1, only odd powers. But remember, we had all of these, you know, the natural log of 2 be raised to the 1st power, to the 2nd power, to the 3rd power, right? We had evens and odds included in this. Likewise, cosine here just has the even powers of x, right? So I think this one's out. Just because, again, we want even and odd powers. Here, tangent inverse, again, only has, odd powers. So I think this one's out. This one, we don't have a factorial in the denominator, right? So we do have all of the powers of x, but we just have n in the bottom, not n factorial. So I don't like this one as much. And okay, the binomial coefficients and x to the n, this thing's strange. It's not this one. No factorials in the bottom there either with this as written. So the only one from this list that resembles my series at all is this e to the x business. So now let's go ahead back here and take a look at this. If I want this to align with this e to the x business, remember I just need one x being raised to the nth power divided by n factorial. And if I can get something like this, where whatever this x is, then this would be equal to e to the x. So right now I have a couple of things being raised to the nth power. And so I want to just kind of smash these together, right? Which you're allowed to do with these powers of, these raised to the nth power, right? This is just going to be negative the natural log of 2. This is essentially this whole distributing thing, but backwards. It's one of our properties of exponentials. And so our x value here is going to be e to the negative natural log of 2. And of course, this can be simplified down if you'd like. The way that you would do that is by using the power rule. Then the e's and the natural logs would cancel. And you'd get 2 to the negative 1st power, which is the same thing as 1/2. So it turns out that this series right here, first of all, it converges, and it converges, better yet, to 1/2, right? We found the sum of the series. All right. Okay, with that, I mean, I have one more of these, but let me pause really quick and see if there are any questions on this sort of stuff. No raised hands. Any in the Q&A, you on?
Yeah, why isn't it a logarithm function?
Why isn't this the logarithm function? Well, let's go back and look at the logarithm function really quick here, so we don't have to derive it again. So here's our logarithm function and the series expansion for this. So, I mean, it does have this alternating piece, which I like. It does have all of the different powers of x, right? The evens and the odds are both are both included here. But the main issue that I have with this is that we're not dividing by n factorial here. In our problem, we're dividing by factorials. And if you try to align this with the natural log, you're just dividing by n. There's also a few other things I would be worried about: the alternating pieces lining up correctly, and also the fact that this starts off at 1 rather than 0. So there's a few other smaller things, but my main concern here, one thing that really can't be reconciled so well, is the fact that you have just an n in the denominator and not an n factorial. That's really the deal breaker.
And I was asking where did the -1 go if it became 1/2?
So the -1 got combined inside of raised to the nth power. And notice that that traveled here, right? So when we replaced our x's in our e to the x as well, so it exists there. And then the question is, well, it seems like whenever you have an e and a natural log, these things should simplify. And they do, but that negative is actually standing in our way a little bit. Remember, if you have something that looks like e to the natural log of u, then because these are inverse functions, you get just u. But this isn't true if you start sprinkling in extra things, right? So if you put a 3 there, this is not equal to 3u. That's off. Or if you put a negative here, right? So long, if you start obstructing, right, and you don't have kind of back-to-back e and then natural log, it doesn't work out. And so you need an e and a natural log, being applied to one another, or kind of back-to-back sort of deal. And so you need to get rid of that negative. And remember, there's a way to get rid of that negative, right? You can kind of use the power rule for logarithms to turn that coefficient into a power. And then you would get 2 to the -1st power. Good. Let's go ahead and take, looks like there's some folks with raised hands. A few quick questions, and then we really owe it to ourselves to get on to some more stuff here.
All right, can you hear me?
Yeah, sure can.
All right, my question is, for questions like example 13, is there always going to be a Maclaurin series that we can relate it to?
For this class, yes. In general, I mean, it kind of, if you just start scouring the internet or something like this for various series trying to figure out what they sum up to, no, not necessarily. But any reasonable problem that we give you in this class, yes.
All right, thank you.
Yeah, no problem. One more. Kenny, you have the floor.
Hello. So basically, like, for that, I guess, like, formula you just did, no, I guess, I don't know how to call it, the equation you just did, e to the ln of 2 to -1. I get how you like rewrote it because of the natural logs rules, right?
Yes.
But I'm just confused on like how do you introduce like the e? How you just like said like, okay, I'm gonna put this inside of the formula and like raise the ln of 2 like to the top. It's just so confusing to me.
Yeah, I mean, this is something that takes some practice. But again, kind of, we first rewrite it in the sigma notation, and then we compare our sigma notation here with well-known Maclaurin series. So that was the bit when I changed over to this PDF here, and I just kind of went down the list and I say, which one of these series here aligns most, closely with what I have. And so as we went through here, we saw, okay, we have a bunch of, various x's raised to different powers. Sometimes you just have the odd powers. Sometimes you have just the even powers. So like for sine and for cosine, those are going to be out. Oops. This one right here, because notice that we have all of the different powers, raised to the first power, oops, raised to the second power, raised to the third, raised to the fourth. So it's not solely odds and it's not solely evens.
And
So
is that is that table that you just showed, is that kind of like a reference that you would use for like series like this, I guess?
Yeah, exactly.
Okay,
Yes.
cool. That makes sense. Thank you.
Yeah, definitely. Good. So with that, actually, I guess I can stay here now. Let's do one more very famous one here. This one, it's kind of, you need to know that you should be looking at tangent inverse. So tangent inverse will help us evaluate out this series here. Let's go ahead and, well, it's just on this sheet here. But of course, remember the tangent inverse, we can also derive ourselves, right? It's just the integral of 1 over 1 plus x squared. So you could just use this bit up here, right? And you'd have to do a little bit more work, but you could recover this same formula here. So, okay, notice that they're just odd powers, right? You're dividing by 2n plus 1, and you have this alternating piece. So let's go ahead and use that. There it goes. So tangent inverse of x is going to be equal to summing up from n equals 0 to infinity, this alternating piece, and we have x raised to odd powers divided by odd numbers. And so you can see that we are actually getting, something quite similar to this. We have the alternating, we have the denominators are just kind of all of these odd powers, right? 5, 7, 9 sort of deal. What do you think that we should plug in for x in order to make this perfectly line up? Yeah, notice that in all of the numerators, we'd have 1, 1, 1, 1. Even we have here for our first one, also a 1 in the numerator. So in our numerators, right, we have to have something that when we raise it to the first power, it's 1, something that when we raise it to the third power, it's 1, something that when we raise it to the fifth power, the seventh power, the ninth power, or any odd power, it's always 1. And so yes, x equaling 1 does a great job of this. So this becomes tangent inverse of 1 is equal to this summing up from n equals 0 and beyond, the alternating piece 1 divided by these odd numbers. Again, they're alternating and all that sort of stuff. What is tangent inverse of 1? Anyone remember? What angle would you plug into tangent and it would output 1? Yeah, so tangent inverse of 1 is pi over 4. And this is why this is a very famous series. This is actually one of the first ways that you can reliably calculate pi, kind of historically, right? So they knew this fact, that if you just kind of summed up all of these reciprocals of odd numbers and you had them alternating sort of deal, that this would give you pi over 4. And so if you wanted to calculate out pi, you would just take that result and multiply it by 4. And so this right here is a good way of approximating pi. Turns out there are other kind of faster ways of approximating pi, but kind of historically, this is one of the first that was discovered. Okay. Let's go ahead and do a few more here. I want to kind of showcase here that you do have to be a little bit careful with these, right? If you're going too fast, notice how similar these are. The only difference here is with this 2n factorial, right? Here we have 9 to the n multiplied by 2n factorial. And then over here, we have 9 to the n, and then the 2n, all of it is inside of the factorial. And so I'd like to show you the sum of these two series and kind of how they differ here. So this first one, let's go ahead and do a quick rewrite. I'm going to take out this 1/2. That's constant in all of them. I'm going to gather all of the stuff that's being raised to the nth power. So let's see, we have a -1, we have a 4, and we have a 9 in the denominator. That's all being raised to the nth power here. In the denominator, we have n factorial. So can someone tell me, of all of our series that we have, that table of Maclaurin series, what does this most resemble? And yeah, I already see it in chat. It's the boring one. It's the same one that we've seemed to be doing over and over again. It's E, right? So it's just E where we have our specific value of X, right? Because for E, you have X to the N is this -4/9. So this is going to converge to 1/2 times E to the -4/9. But I want to showcase how this is significantly different. And kind of the point of this is to show the difference between these two right here. For this one, notice that you have 2n factorial in the denominator. So you're only going to be having even things in the denominator. So let's look for functions or series here that have a 2n factorial in the denominator, because without that, it's pretty hard to recover this. So, okay, again, kind of these first couple are out. E is out because, again, it just has n factorial in the denominator. We want to have, you know, kind of just the even 2n factorial. Sine is out, right? It has 2n plus 1. That's going to be the odds. Cosine. Cosine is looking pretty good, right? Cosine has this 2n factorial in the denominator. It has the alternating piece. That's good. All right, x raised to the 2n power. Anyone else have this 2n factorial in the denominator? No. And so I think it's going to be something like cosine. So let's go back here. And again, kind of the only one that has this 2n factorial in the denominator is cosine. And so remember, cosine of x looks like this. Cosine of x is summing up from n equals 0 to infinity of, it's an alternating thing. And then you have x to the 2n divided by 2n factorial. So my problem here, we have summing up. Let's leave the alternating piece out here. And then we have 4 to the nth power divided by 9 to the nth power divided by 2n factorial. So the question is, how can I write this as this? Right? I need something that when I raise it to the 2nth, we get 4 to the n divided by 9 to the n. And yeah, I already kind of see it here in chat a few times, that if you go ahead and spend one more line here, -1 to the n, you could write this as 2/3 squared. That's not my best 2's there. Let me go ahead and rewrite that. Right, so 4/9 is the same thing as 2/3 squared. And now each one of those is being raised to the nth power. And so remember, whenever you have powers raised to more powers, they multiply together. And so this is indeed 2/3 raised to the 2nth power. We have the 2n factorial still in the denominator and all that sort of stuff. So here we can see that our value of x is just 2/3. So our series now converges to cosine of 2/3. So again, the reason why I bring these up is that if you're going too fast, you can miss things. And so do be careful with reading these sometimes. All right, so that's a lot of the summing up series stuff. Let's do a few of these limits. We saw a few of these already in the video here, but the big thing that I really want to get to here are these last couple of problems, right? These are some where you don't have any elementary antiderivatives, but we can evaluate these with power series. And so these are the things that I'm I really want to get to today. So Maclaurin series, in order to evaluate out this. So of course, this one's simple enough. We've seen lots of ways to do this, right? We have a Calc 1 way of doing this. We could use L'Hopital's rule for this, but I want to illustrate the method of using the Maclaurin series in order to calculate this out. With the Maclaurin series, right, you always kind of take the piece that we, again, from the table there, that we know how to evaluate out with the Maclaurin series. So here we have sine of 3x. So if I wanted to evaluate out sine of 3x with our Maclaurin series, this is going to be summing up from n equals 0 and beyond. And right, we have 3x here. The sign is going to be alternating, and we only have the odd powers. So we have 2n plus 1 here, and we have 2n plus 1 factorial in the denominator here. And now normally if you just had sine of x, right, you'd put an x here. But now because we have 3x, right, we're going to substitute in, and we're going to put a 3x here. Let's go ahead and evaluate out, some of the first terms here, just to kind of see what this is looking like. So I'm just going to evaluate maybe 3 of these things. So if I plug in first n equals 0, so that's going to be my first one here. Let's see, -1 to the 0th power is going to be 1. If I raise anything to the 0th power, well, we have to be careful, right? Because it's 2n, that's going to be 2 times 0 plus 1. This is actually going to be 3x, right? That plus 1 kind of saves it a little bit. And then when we divide by, let's see, the 0 plus 1 factorial, that's going to be just 1. All right, next up, let's plug in n equals 1. So first of all, the alternating piece is going to give us the negative, right? Now that we plug in n equals 1. Here we're going to have the 3x that's being cubed. And let's go ahead and divide that by 3 factorial. So again, plugging in n equals 1. And last one here that I'm going to write out, n equals 2. When I take my alternating piece, my -1, and I square it, that gives us +1. And when I plug in 2, let's see, we're going to have 3x to the 5th power, and we're going to be dividing that by 5 factorial. Of course, this continues on forever. So let's go ahead and see here, right? My goal is to say something about sine of 3x divided by x. And mainly we're interested in what is the limit as x goes to 0 for this. So let's see, we're going to go ahead and take our Maclaurin series for sine of 3x, and that looks like it's 3x minus, let's write here, 27x cubed divided by 6. I know that that could simplify a little bit down, but that's what we'll just write it as for right now. Here's what, 243x to the 5th divided by 5 factorial, that's 120, and it keeps on going. And if I was to go ahead and divide all of these things by x, well, there's going to be a lot of cancellation that happens here, right? We're going to have a 3, x divided by x. Then we're going to have minus 27x squared divided by 6. Then we're going to have plus 243x to the 4th divided by 120, right? 1x cancels from every single term when we take this full, this infinite series and divide each term by x. And so now as x goes to 0 here, right? Again, we're taking the limit as x goes to 0. And sorry, I did a bad job. I should include this along here, right? We're taking the limit as x goes to 0 for all of these things. Notice that all of these terms over here still have x's in them. And so as x goes to 0, all of those terms are going to go away, right? Because here we have like x squared, x to the 4th, then you're going to have x to the 6th, x to the 8th, x to the 10th, so on and so forth, right? And so all of those terms are going to go away, and we know that the answer is going to be 3. And so whether you use your Calc 1 method for evaluating this, or if you use L'Hopital's rule, or if you use a Maclaurin series, which we were interested in illustrating here, the answer is always 3. This one I'm probably going to skip in the interest of time. If we have more time, I'll come back to this one. But this is one that would be a real pain. It would take actually 4 iterations of L'Hopital's rule in order to evaluate this out. However, if you use your Maclaurin series, and in particular for cosine here, that's the only thing that's not a polynomial already. But if you use your Maclaurin series for cosine, turns out that this is faster to evaluate with series than it is with 4 times L'Hopital's rule. Okay, with that, let's go ahead and see what kind of questions are out there. Anito, you have the floor.
Just a quick question for the the limit as x approaches 0 for sine of 3x over x.
Yes.
Is this related to that one like rule or law or whatever, where like the limit as x approaches 0, like a sine of x over x equals 1 or something like that. I forgot what it was.
Yeah, exactly. So
Okay,
that would be the Calc 1 way of evaluating this out.
all right, for sure. Yeah, thank you.
Any questions in the Q&A, Yuan?
One is asking, why do we divide the series by x?
Well, that's what the problem, as it was posed to us, right? It had this division by x. And so that's why we do it, is just because that's the thing that we're interested in evaluating. If that x was not there in the problem posed to us, we wouldn't do it. Good. So here's some here that I'd like to showcase. Again, kind of power series, one of their main uses here is that even with all of our power from chapter 7, again, there are some things that we just cannot evaluate. There's just some functions out there that do not have elementary antiderivatives. In fact, I think this is a worthwhile. I'm going to switch over here to my desktop really quick and show you guys. I'm just on Wolfram Alpha. This is as good as any, that I'm going to integrate sine of x divided by x. Let's just see what it gives us. Integrate sine of x over x. Here's the answer. Psi of x. So you can see that, you could spend a year, you could spend your entire lifetime, trying to evaluate out this integral using all sorts of things like integration by parts and u substitutions. You can get really creative with all this sort of stuff, and none of them are going to work out. It just turns out that this thing right here, it doesn't have an elementary antiderivative. There is no way to integrate this using any of the techniques that we know and love. And there's no result that you get that's in terms of any of the functions that we've defined previous to this. So you just have to define a new function, and it's psi of x. Quite literally, the SI stands for sine integral. So that's the psi of x there. And so, okay. However, right, with our series, it turns out, right, we can get at least a good approximation for this thing. And so let's go ahead. And of course, it will be equal if you include out the entire series. But quite often, when you're actually calculating out something, you stop after, so many terms, and you just are happy with your approximation, right? Maybe once you have 100 digits of accuracy, you're happy. So, the next problem here when we use this is, again, something that doesn't have an elementary antiderivative, but you want to know the area under the curve for this thing, right? Our normal technique of, hey, we'll find the antiderivative, then plug in 0 and 1 and subtract. That's not going to work here. And so this is where the Maclaurin or the Taylor series are very powerful. So in order to evaluate this out, we're going to use the sigma notation, right? We're going to use the full power series here for sine of x. So I'm going to write sine of x is equal to, and well, we just did this one. So it has the alternating thing. It has odd powers of x, and you divide by odd factorials. There you go. And so we're going to build up our function first. So the next thing, there we go. iPad wasn't responding. We're going to go ahead and divide through by x. Right? We're going to build up our function that we're tasked with integrating here. So if I divide through by x, well, I'm going to go ahead and push that inside of my sum here. And I'd like to argue that this just becomes x to the 2n. And the reason why is, right, you had 2n plus 1 on top, and when you divide through by x, right, there's some cancellation that happens. You have one x on bottom, and you have a lot of x's on top. One of them is going to get canceled off. And so that's why this just cancels, and you get x to the 2n. Still, you have division by this 2n plus 1 factorial. Which, by the way, again, sometimes the sigma notation stuff is a little bit complex, to look at all of this. So it's not a bad idea if you're, not happy with this, kind of sigma notation stuff 100% yet. It's not a bad idea to kind of carry out a first few terms, just to kind of really see what this thing is looking like, right? So if I write out the first few terms of sine of x, remember it looks like x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus so on and so forth, right? It has the alternating piece. It has just the odd powers of x divided by odd factorials. And so if we go ahead and we divide through by x across the board, right, we're going to have 1 minus x squared divided by 3 factorial plus x to the 4th divided by 5 factorial minus so on and so forth, right? So you can kind of see that there's just the even powers of x now. Everything else stays intact, but you just have the even powers of x. Okay, now we're ready to go ahead and integrate this thing. And again, we know, from Wolfram Alpha and from mathematicians who have come before us that you can't integrate this thing with integration by parts or really anything else. And so the integral here is you just call it psi of x. But if you'd like to approximate this, right, well, we can integrate these things term by term. And so when we go and we integrate them, well, let's see, I'm going to keep my constants or my coefficients off to the side here, right? These are just along for the ride. And so, oops, 2n plus 1 factorial. And when I integrate x to the 2n, well, we're going to use the power rule, right? We're going to raise up our power by 1. And we're going to divide by that new exponent there. So that new exponent is going to be 2n plus 1. So this right here is my final answer. And of course, if you want to see what it looks like, I think kind of writing out a first few terms really helps with that. So if I integrate, right, we're going to have x, then we're going to have, let's see, x cubed divided by, and again, kind of the factorials are along for the ride, the alternating pieces along for the ride, but you do get this 3, right? When you take the derivative of this, you need to get back to where you started there. And here we would have x to the 5th divided by still the 5 factorial. The factorial's along for the ride, but you get this extra 5, right? And then it just kind of continues. So then if you wanted to, evaluate this, have a definite integral, and you wanted to figure out maybe the area under this curve here, you could plug in specific values into your x, right? Plug in things like 0 and 1. In particular, that's what we're going to do down here. So this is one of the main uses, right, that really can't be replicated by L'Hopital's rule or anything else, and kind of why, Taylor-Maclaurin series have quite a bit of power, right? Again, there's just some functions that you can't integrate in any other way. So you don't get a closed form integral, but you can still write out the integral as in terms of a series. So you have this, and, by the way, we could talk about the interval of convergence and all that sort of stuff, right? You can calculate that out with the 11.8 method here and figure out what's the interval and radius of convergence there. All right, let's see what kind of questions are out there, and hopefully we have time to at least talk a little bit about example 19. Teresa, you're on the floor. You have the floor? That's probably better.
Mine is related to the fact that we found the antiderivative. I just want to know why, even though the -1n to the power of n, all of those are still variables, why we don't take the antiderivative of that.
So you have to be careful, right, what you're taking the derivative with respect to, right? So when you say n is a variable, sure, when you write it in the sigma notation, it is because it represents, right, different powers, right? So when we write it like over here, you can see that n is changing as you write these things out. But with respect to x, it's constant. So these things are constant with respect to x. And so when you go and you integrate with respect to x, right, there are some constant, right? Maybe it's a 2, maybe it's a 4, maybe it's a 7, right? But they're constant with respect to x. As x changes, they don't change. And so when you integrate with respect to x, you just treat them as a constant.
So it doesn't matter that even though the sigma goes from n equals 0 to infinity, so it is changing in that aspect. It's not changing at all from the original to the new antiderivative because we're finding the antiderivative of sine of x over x.
Exactly. Our antiderivative is with respect to x. And so they're all constant with respect to x. And that's kind of why I think that even though, folks will tell me that these bits right here aren't necessary, And it's true, they're not necessary. This isn't my final answer here, but I think this really helps to illustrate that those n's, while they do change, you know, and help you write out the full infinite polynomial, once you've written it out, like, you know, kind of thinking about if I just went from this here down to this here, right? Once you've written it out, those n's are constant, right? Literally that n is 0, and there the n is 2, and there the n is 4. And when I go and I integrate, right, I just integrate each piece. And once I've written them out, right, they're constants. And so you can kind of clearly see here, this x squared, I don't have to worry about all the different possibilities of what n takes on eventually. Here, when n equals 2, we have x squared, and I can integrate x squared.
Okay, thank you.
Yeah, definitely. Let's see here. Any other questions? Michael, you have the floor.
Hello again. So I wanted to ask, why can't we take the antiderivative of sine x over x?
Give it a go. It's just, yeah, it doesn't work. No matter what you try, no matter what technique you develop, right? There's just not, you know, any antiderivative for this. It is in general very difficult to classify which functions have elementary antiderivatives and which ones don't. Mathematicians have done the work, and we do have, you know, we know exactly which ones don't have elementary antiderivatives, but this is some very high level mathematics. So at this point, right, it's just kind of, well, you can try it and it doesn't work out. And no matter what you try, it doesn't work out. And so it's at least somewhat convincing that there's not going to be an antiderivative.
All right.
Yeah, sorry, I can't give you the full details, but it gets very, very messy. Okay, well, it's 2:40. I'm going to do this one anyway. If you guys have to leave, by all means, go for it. But I'm going to do this one a little bit fast here. Again, this is one, go to Wolfram Alpha, go wherever you'd like, you know, that does integral calculators or whatnot, and try to evaluate out just the integral of e to the negative x squared, and it doesn't work, right? There's no elementary antiderivative for this. However, using this fact that e to the u is equal to summing up from n equals 0 to infinity of various powers of x divided by n factorial. Oops, I forgot I used u as my variable here. We have this. And so in particular, I'd like to substitute in, instead of u, I'm going to put negative x squared. So e to the negative x squared is going to be equal to summing up from n equals 0 and beyond negative x squared raised to the nth power divided by n factorial. It's always important, right, especially when you want to do some derivatives or antiderivatives and stuff like this, to really separate out and get all of your coefficients together and all of your variables together. And so I'm going to go ahead and take a line here and do just that, right? Of course, my n factorial here, that's going to be a coefficient. We have this alternating piece, right? This -1, and it's being raised to the nth power. So I'm going to go ahead and write that, the alternating piece over here. It's a coefficient. And then all the stuff that has x's, right? We have x squared, and it's also being raised to the nth power. And remember, whenever you have powers raised to more powers, they multiply. And so you get x to the 2n. Now we're set up and ready to integrate this thing. And so when we integrate this, we go ahead and just write it down first, that we are integrating this with respect to x. Well, we have all of our coefficients are along for the ride. They're just fixed numbers there. And then when we integrate with respect to x, we raise up our power by 1 and we divide by that new power. Again, this is just the power rule here. Now, in this case, right, we were interested in evaluating out, right? This was a definite integral from 0 to 1. So we'd like to go from 0 to 1 here. Well, I just did the antiderivative. And I'd like to plug in 0 and 1. Can someone tell me if I was to plug in 0 in for this thing, right? What do I get out when I plug in 0 everywhere I see an x? Here's all my x's here. Yeah, we're going to have a lot of zeros raised to different powers and divided by interesting things, but 0 times anything is 0. And so the only piece here that contributes is going to be this. And when I plug in 1, well, 1 raised to various powers is awfully boring. It's just 1. And so this right here will be my final answer. And of course, you can write this out as many terms as you want, by the way. You can do just, 5 terms, you can do 10 terms, you can do 100 terms. You can ask for any sort of, if you want this accurate up to 10 decimal places, right? You can evaluate out the series far enough so that way you have 10 places of decimal accuracy. Or if you want to do 100 places of accuracy, right? You can make this as accurate as you want. And so that's the nice thing about this. So even though there's no elementary antiderivative, you can solve problems like this thanks to Maclaurin and Taylor series. All right, that's going to be where I stop the recording and cut it off for today. Thank you for those.